You know, every single time you send an email or buy something online, or heck, even just scroll through your social media feed, you're depending on this invisible shield. It's this whole system of digital locks and keys, and it's literally the foundation of trust on the internet. So how does this invisible lock actually work? Well, let's dive in and find out. Okay, so here's our game plan. First, we're going to talk about why keeping secrets online is just so hard. Then we'll check out this early kind of spy movie solution that involves a handcuffed briefcase. From there, we'll get into the real magic, using 2 keys instead of just 1. We'll even see it in action with the famous duo Alice and Bob. And finally, we'll see how this one simple idea blows up to become the foundation of trust for the entire internet.
So, where do we start? Well, it all kicks off with a really simple, but honestly, a really profound challenge. I want you to imagine something. Think of the internet, not as a bunch of private tubes, right? But more like a massive, super crowded town square. And messages are just being passed hand to hand, out in the open for everyone to see. So the question is, how in the world do you send a secret note in that environment when you know anyone could just snatch it? That is the fundamental puzzle we've got to solve.
All right, so our first crack at solving this puzzle, it leads us to an idea that feels like it's straight out of a spy movie. We're talking the handcuffed briefcase, and it's actually the perfect way to understand something called symmetric encryption. The concept here is super simple, really. You have one key, just one. You use that key to lock a box, and the person on the other end, they use the exact same key to unlock it. Since you're both sharing the same single key, we call it a shared secret. Makes sense, right?
And, well, this brings us right back to that spy movie problem, doesn't it? Okay, so you've locked your secret message in a briefcase. Great. But now what? You've got to get the key to your contact across town. You can't just stick it in the mail, obviously. It could get intercepted. So you end up having to handcuff the key to a courier's wrist. And that is the core problem right there. Sharing the secret key is just as difficult as sharing the secret message in the first place. So here's the deal. You've got this crucial trade-off. On the one hand, symmetric encryption is lightning fast. I mean, super low processing overhead. But on the other hand, it has a massive scalability problem. Just think about it. Imagine you're a business and you need to talk securely with 1,000 customers. You'd have to manage 1,000 different secret keys. It's this tangled mess that's just begging to break. It is a total logistical nightmare. So if having one key is the problem, what's the solution? Well, and this is kind of counterintuitive. The solution is to use 2 keys. This is where we get into something called asymmetric encryption. And believe me, this is where the real magic happens. Okay, so with asymmetric encryption, you generate a pair of keys. Now, these 2 keys are mathematically linked, but they have totally unique complementary jobs. Think of them like a perfectly matched set. One key is designed only to lock things, and its partner is the only key in the whole world that can unlock it. So here's how it all breaks down. You've got a private key. This is the one you guard with your life. You never, ever share it with anyone. Then you've got its partner, the public key. And this one, you can shout it from the rooftops, post it on your website, give it to anyone who asks for it. Why? Because its only job is to lock messages, messages that only your private key can ever unlock. And this quote, man, it just perfectly nails the core security principle. The math behind these keys is basically a one-way street. Someone can have your public key, the one for locking, but there is no way at all they can use it to reverse engineer and figure out your private key. It's kind of like having the blueprints for a certain model of a lock. That doesn't really help you craft the one unique key that can actually open it, does it? So this table really lays it all out, side by side. You've got symmetric. It's the speed demon, uses one key, but its Achilles heel is, how do you share that key safely? Then you've got asymmetric with its public and private pair. It's a little bit slower, yeah, but it brilliantly solves that key sharing problem. But here's the really clever part. In the real world, we use both. It's amazing. Systems will use the slower asymmetric method for just one tiny job, to securely exchange a temporary symmetric key. And then that symmetric key takes over and does all the fast, heavy-duty encryption. It's literally the best of both worlds. Okay, so theory is great and all, but let's make this real. Let's make it concrete. We're going to walk through how this whole thing actually works with the 2 most famous people in all of cryptography, Alice and Bob. Really, it's like a simple, elegant dance. Check it out. Step 1, Alice creates her 2 keys, the public and the private one. Step 2, she gives her public key to her friend, Bob. Step 3, Bob writes his message and uses Alice's public key to scramble it into total gibberish, what we call ciphertext. Step 4, he sends this scrambled message to Alice, right out there on the open internet. And finally, step 5, Alice uses her private key, the one nobody else in the world has, to unscramble it and read the original message. Simple as that.
And this is the payoff. This is the whole point. An eavesdropper, let's call her Eve, that's the tradition, she can intercept the message. Eve can even have a copy of Alice's public key. And you know what? It doesn't matter. Not one bit. Without Alice's private key, that message is just digital noise. It's completely, totally secure. Okay, so managing keys between two friends, Alice and Bob, that's one thing. But how do you scale this up? How does this system work to secure the entire internet with billions of users and devices all talking to each other? Well, that's where something called Public Key Infrastructure, or PKI, comes into the picture. Now, PKI isn't just some app or a single piece of software. No, it's the whole system, the entire framework. A good way to think about it is like the government department that issues passports. PKI provides the rules, the verification process, and the trusted authorities that make sure a public key really belongs to who it says it belongs to. So, at the end of the day, PKI is the answer to that big scalability question. It's the framework that lets a huge company manage keys for thousands of employees. But more importantly for you, it's what allows your web browser to trust that when you connect to your bank's website, you're really connecting to your bank and not some imposter trying to steal your password. And this management system, it tackles some really crucial real-world problems. For instance, it uses these trusted third parties called certificate authorities, or CAs, to basically vouch for people's identities, to verify that a public key is legit. It also handles tricky situations, like something called key escrow. That's just a fancy way of saying it creates a secure backup of a key, so a company doesn't lose access to its own encrypted data if, say, an employee quits. It's all about building a robust, reliable system of trust. All right, let's wrap this up. Let's pull it all together. We started with a simple one-key lock, symmetric. Super fast, but with a big flaw. Then we moved on to the two-key system, asymmetric. This elegant solution is the bedrock of modern security. The rule is just so simple. Public keys lock, private keys unlock. And finally, we saw how PKI acts as the global referee for all of this, managing all these keys to create the system of trust we all rely on every single day. So I want to leave you with one final thought. This system, it's not some abstract technical thing. It is literally all around you. It's that little padlock icon in your browser's address bar. It's what keeps your text messages private. It's what secures your online banking. Now that you know the secret, now that you know how the lock really works, I'm curious. How many places can you spot it in your own daily life?